So very good afternoon, everyone. And a quick check with Rashik ji. Everything is good. My voice is clear. My video is clear, Rashik ji.
All good to go, sir.
Thank you so much. So very warm welcome to today's webinar, The Next Frontier, AI, ML, Drones, and Integrated Geophysics for Subsurface Challenges. I am Sanjay Rana, and I'm truly delighted to see such a diverse audience joining today. We have engineers, we have geoscientists, we have technologists, planners, consultants, students. So, a wonderful, diverse audience we have for this webinar. I look forward to a great session together. So, today's session is going to explore how we are entering a new era of subsurface investigation. We'll discuss how artificial intelligence, that's what we call AI, machine learning, ML, drones, and integrated geophysical methods are not just enhancing how we collect data, but also how we interpret, visualize, and act on it. So, whether it's infrastructure health, energy exploration, environmental risk, the integration of these cutting edge tools is redefining both speed and precision in geophysical workflows. So, over the next hour, I'll be sharing insights, case studies, and emerging frameworks that highlight how these technologies are converging, creating high resolution 2D and 3D models, enabling real time monitoring, and ultimately supporting smarter and faster decisions in the field. Please feel free to post your questions in the chat box. In last two webinars, we have observed that we have overshot time a bit. So I'll really like to take most of the questions from the chat box. If there is time, then only we'll go for live interaction. So please post your questions in the chat box and we'll take it towards the end of the session. And like every time before we begin, I would like to sincerely thank the team who made this webinar and these webinars actually possible. Mr. Rashik Kathuria, Ms. Pragya Sharma, Ms. Anushka Batra, Ms. Suchetna Banerjee, and Ms. Priya Mohini. Your continued support helps us push the envelope with each session. So with this, let me start sharing my screen and walk you through the presentation. Right. All right. Perfect. So I think my screen is visible. Rashik ji, quick check.
Sir, it is.
Perfect. Great. So this is part of the 5 webinar series which we are having. This is pre-conference webinar series before we get to our near surface geophysics conference in November. The first one was on dam safety. Then we had one on urban geophysics. Then environmental cleanup was the last one. And today we are going to talk about AI, ML, drones, and integrated geophysics for subsurface challenges. And then we will, the last one in the series will be powering the energy transition, geophysical techniques in pump storage, solar, and wind siting, which will be on October 18th. We do it every alternate Saturday. If you have missed any of these, you don't need to worry about it. Just write to us, and all these webinars are recorded, and recording will be provided to you, and you can go through the recording, ask your questions on the email which is available to you. So you have not missed anything. Of course, live is always more exciting. We can interact, but you can definitely go for the recorded ones. Before I start the webinar, a very small introduction to the company which I represent. Uh, I'm from Parson. Parson is a ISO certified geophysical company. We are the largest engineering geophysical company in the country, and we are known for bringing various cutting edge technologies to the country from time to time. And that's listed here. I'm not going to go through the list. Our main strength, of course, is our people who are highly experienced and trained. We are an Indian multinational, so we have offices in India, Bahrain, Saudi Arabia, and Singapore. And through these offices, we are working in more than 14 countries around the world. I'm a geophysicist by profession, around 35 years of work experience. I graduated in 1990 from University of Roorkee, which is now IIT Roorkee. I started my career with the government, initially with the state government, and then I went on to atomic energy, the central government. And 1995, I started a company in the field of near surface geophysics, which was the first company in the country in this particular sector. And since then, I am just doing that. As on date, we have completed more than 2,000 projects around the globe. Standards are very important to promote any technology to make it done in the right way, so to say. So I'm involved with BIS, that is Bureau of Indian Standards, in 6 different codes which we are developing. IRC, Indian Road Congress, Tunneling Association of India, and INDSCT. And I'm the principal author of 4 of these codes and documents which are listed on your screen here. So that's a very, very short introduction about myself. And like always, before we get into the topic of the day, I always go for a very small introduction about geophysics, because there are many people who are joining who are not geophysicists, who might be engineers or coming from a different background. So I always like to give a very brief introduction about what geophysics is. And for me, this is the best way to explain what geophysics is, because this is something by which you can even explain it to your 5-year-old child. That is, we all know medical imaging, right? We know ultrasound, we know X-ray, we know MRI, we know CT scan. So what are we doing here is we are sending different kind of rays and waves inside the human body to create an image of what's inside. Now, that is exactly what we are doing in geophysics. That is, we are sending different kind of rays and waves inside the earth or a structure and trying to create an image of what is inside the earth, right? So it is pretty similar to medical imaging. Of course, more challenging because body is very well defined. We know where are joints, where are different organs. So interpretation of medical imaging data is much easier compared to interpretation of geophysical data. But yeah, that's a topic for some other day. But this is the best way to understand what geophysics is. That is, we are sending different kind of rays and waves or measuring naturally occurring fields. It can be magnetic field, it can be gravitational field, it can be telluric field. So by doing this, we are trying to understand what's inside the earth. So that's a simple way to understand what geophysics is. And why is it so important? Because traditionally, we have been trying to collect data based on drilling, primarily drilling. But drilling gives you data at a discrete point. It gives you very precise data. There's no doubt about that, all right? Drilling gives you very precise data, but it gives you data at one particular point where you are doing the drilling. In the process, you definitely miss a lot of information between your drill holes. And that's where you do assumptions, right? You assume things. Secondly, geophysics is very rapid and cost effective. When we say rapid, today using airborne and heliborne methods, you are able to cover hundreds and thousands of line kilometers in a single day. So that's the speed of operation. Cost effective, it is almost the same comparison as you can have, for example, between an ultrasound and a surgery, right? So geophysics is much rapid, cost effective. And then, sorry, I just went to the next one. All right. And before this, I will again have to stop sharing a bit. This is something which happens with me every time, that when I start sharing my screen, I forget to put the option of sharing the sound. All right. So it's non-destructive. Obviously, you're not doing any drilling, so it's totally non-destructive. At the same time, it gives continuous information. That's a major point which we need to understand. For example, look at this schematic diagram here. You have different, a void here, a limestone pinnacle, so they are geological features. You have various anthropological objects here. Any amount of drilling you do, what are the chances of actually picking all these objects and all these anomalies from one end to the other? Chances are 1 in million or 1 in thousand, depending on what is the size of these objects and what is the drill spacing between your boreholes. Whereas if you do a good geophysical campaign, a well-designed geophysical campaign, you can actually cover it from one end to the other in a continuous manner. So continuous information is one of the biggest point about geophysics, okay? And please remember that after this presentation, never go back with an impression that geophysics replaces drilling. It does not replace drilling. As I said, drilling gives you very precise information at the point where drilling is being done. Geophysics is giving you physical properties of the material. You cannot get more than physical properties just by geophysics alone, and you need so many things of a particular formation. You need, for example, C, phi, chemical composition, etc., 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 right? What geophysics does it, that it optimizes your drilling. So instead of doing random drilling, let's say every 50 meters or every 100 meters, if you do a good geophysical campaign, you can reduce your drilling from 100 to maybe 5 or 10. So you can optimize your drill holes right at the place where you need more information, where some anomaly has been detected using geophysics. So geophysics does not replace drilling, it optimizes drilling. That's a very important point to understand. And it leads to minimization of surprises. Because when we talk about geological surprises in any project, geological surprises are nothing but something which is coming up which was unanticipated because it was uninvestigated. So once you have got continuous information, of course, there is no surprise, or at least there are minimum surprises. So minimization of surprises. And it's always good for early stage application. That is at the project planning stage, at the time of when you're starting your project, that's the time it should be done so that the entire design can be done properly, drilling can be done in the optimized manner, and the project is safe. So this is something which is very, very important to talk about when we talk about geophysics. Okay. Now, if you want to learn more about geophysics, there's a great opportunity coming up, and that's third Indian Near Surface Conference and Exhibition. That's what I talked about. That is where we are going to, we are leading to through these free webinars, because this is where the finest minds of the world, finest brains of the world in the field of near surface geophysics are going to be there. And yeah, it's a great opportunity to mingle and to talk to them, to listen to their technologies. Here is a very, very brief video explaining this.
Greetings. We are very excited to share that the third Indian Near Surface Geophysics Conference and exhibition is coming up this November. It is being organized by ACO Foundation Academy in collaboration with EAG. The event will take place from 12th to 14th November 2025 at the Surya in New Delhi. This year's themes touch on some of the most critical areas from engineering and environmental geophysics to urban mapping and energy transition solutions. From seismic refraction to ground penetrating radar, this conference brings it all under one roof. Two pre conferences are also being organized on 12th November 2025, focused on dam safety and contaminated sites. We will also be presenting the most awaited INSG Awards and Dam Safety Awards for this year. So, if you're working in geoscience, infrastructure, environment, or research, this is where you'll want to be. Please visit our website and register now.
So this is the website of the event, and you can just go and register yourself. I'm sure Anushka will be posting a link in the chat box, so you can use the link also to register yourself. So be there. This is a wonderful opportunity to really learn a lot in the field of near surface geophysics. And if you're already an expert, it's a great opportunity to share your insights with others.
Greetings.
So now coming to the topic of the day, why subsurface investigations are evolving and how modern geophysics is rising to meet the challenge. So let's understand this point. So there is a lot of demand for faster and safer and deeper insights into what lies beneath. Projects are getting more and more complex. We are talking of smart cities, renewable energy, environmental monitoring, much deeper mining. The mines which were shallow have been exhausted. Rapid infrastructure growth. When we talk about even infrastructure growth, if you're talking of cities, we are building in the areas which are already congested. When we talk about smart cities, we have a great need to understand what lies beneath, etc., etc. Renewable energy, for example, pump storage projects, solar projects, so many things are coming up. It's a much more complex situation which is now. And the subsurface data is absolutely mandatory. Without some subsurface data, you cannot go ahead when it comes to doing any project on the surface of the earth or in the underground. Now, challenges which are driving the innovation today is first of all the resolution limits. Okay, so that legacy tools miss deep or narrow targets. We know that if the target is small, if it is very deep, etc., we tend to miss the target. There are areas which are very rugged, remote, or congested, which becomes very hard to scan by normal methods. For example, you're talking of a area which is having a very high level of vegetation. You cannot even go there. You cannot put the foot in that area, or a very contaminated site. Landfills for that matter, right? Our ground geophysics cannot be done in these areas, or for certain areas which are dangerous to go because of any level of any kind of contamination, right? So limited accessibility is another point. And then there are many projects where there's a need for real time data. When we talk about emergency response, the drilling and construction can't wait for the lab results. You need real time data, and that's where now innovation is going. These challenges are being made by being met by innovation. And if we just look at the sectors, you have infrastructure, detecting sinkholes, voids, utilities, buried tunnels. Now, if you just talk a few of them, in various cities, even last webinar was on urban geophysics. We saw photographs of how sinkholes are opening up on the roads, and practically the entire cars sometimes are going inside. Recently, we had a case in Hong Kong of a big sinkhole opening there, right? So detecting of these sinkholes, voids, underground utilities, buried tunnels, in energy, subsurface imaging for geothermal, hydrocarbon, storage, environment, of course, monitoring landslides, contamination, aquifers. So all these sectors, whichever sector you talk about, it requires precision, speed, and scalability. And that comes by innovation, by going to the technologies which are coming up, which includes, of course, drones, AI, ML, etc. So if we just do a very, very brief comparison, right? Legacy approach is based on ground-based methods, all right? Whereas in modern approaches, which we are talking about, we are having UAV-mounted geophysical sensors, right? In earlier approaches, most of the data interpretation is manual, right? Even today, for example, most of the data interpretation is manual. Data processing has gone to a lot of software and all that long time back for that matter. But when we come to data interpretation, it remains manual. Whereas in the new approach, it can be AI powered. Automated anomaly detection is something which is coming up very fast. So instead of just depending on your eyes for the anomaly detection, you are using the power of AI for anomaly detection. Earlier approach, of course, static, slow turnaround results, whereas in modern approach, real time, cloud integrated insights. Work is happening on a site at some place, and the data is can be seen sitting in a different office. Everything is on the cloud. You are able to see the data. You can have 5 different experts sitting in 5 different parts of the world, and they can give their opinion on the data at the same time, right? Legacy approach, single modality of exploration, and now in modern approach, of course, you have multi-sensor, multi-scale data fusion. So a lot of things are changing, and so modern geophysics is less about collecting data and more about understanding it fast and in 3D. So collection of data is one point where, for example, as we said, drones come in picture and all that. But most of the development is happening in the way we look at the data, how we are able to understand the data in a very, very fast manner. So artificial intelligence and machine learning applications, when we talk about, so from interpretation to automation, how AI is transforming geophysical workflows. So I'll just spend 3 slides on understanding the entire artificial intelligence gambit. And then we will, of course, jump to the real kind of real life near surface case studies so that we are able to see how AI is playing its role there. All right. So when we talk about right in the first one, okay, this particular image is very interesting. And in this image, if you see 4 different ways how scientists study the Earth is showing there. So, like looking at weather, ocean, mountains, or climate, each style is a different way to understand how the Earth works. So, think of them as different tools in a toolbox, each one useful for a different kind of Earth problem. First one, which you see, is observational hypothesis driven paradigm. What does it mean is look, wonder, and guess what's happening. So, this is like a scientist going out, looking around, and writing down what they see. So, this is basically observation. Then they ask the question and make guess. That guess is a hypothesis, like why does it rain more here? And after that, they try to test this guess using more observation. So, for example, looking at maps or rain patterns to figure out why some places flood more. So, this is the first approach, observational hypothesis driven paradigm. Then, second one is model driven paradigm. Now, in this, let's build a mini Earth on the computer, right? So, for everything, let's build a model. This model can be a physical model, this model can be a numerical model. So here scientists make computer models that act like Earth. These models simulate things like weather, river, or air pollution. So it's like playing, kind of a sim city for nature, changing things to see what happens. So what will happen if we cut down trees in a forest? So cut the trees and see what's the impact, and the model will tell you the impact. This is the model-driven paradigm. Third one is data-driven paradigm. Now in this, we do not use physics here. We just use data to show us the patterns. So in this, scientists don't start with a guess, right? No hypothesis. They take tons of data, like photos from satellite, temperature number, etc., and let computers find the pattern. So it's like asking Google to find all the places that got hotter last year without knowing where to look, using traffic and pollution data to understand why some cities have more smog. So this is completely data driven. You're not using any physics in this, you're just using lots and lots, tons and tons of data to do that. And then comes model data driven paradigm. So in this, we mix smart guesses with smart data. So this is the newest and smartest method. So this combines computer models and real data. So it's like T-BAM. Model guesses the rules, data checks if the rules are right. So this is the process in which scientists also use AI and machine learning. So it's like giving the earth a robot brain, so to say. Example, predicting floods or climate change by mixing real weather data and computer simulation. So you had model also, you have the real data also, you put them together. And why it becomes so important is because this helps us understand natural disasters, predict climate changes, keep cities safe, protect the environment. So each method like a different lens to look at our amazing planet, and scientists are learning to use all of them together. So if you're a young scientist, all right, if you're a student, so you could think of it like look carefully, make a smart guess, use computers to help, use both data and model to be even smarter. So this is the starting point of AI and how AI is working and what four models we are talking about. Then we come to the next one, and this figure also is very interesting. I've kept these figures because they very beautifully explain the entire process. So this image here shows how AI is helping scientists watch the Earth, that is observation, think about how it works, that is hypothesis, and guess what might happen next, that's prediction. So all of this is part of geosciences. Now let's look at the four boxes which are there. Each one shows a different way AI is helping in studying the Earth. First is data collection, processing, and representation. Okay, so this is getting and organizing smart Earth data. So here we are using satellites, drones, sensors to collect data from Earth, like weather, soil, ocean, etc. Can come from anywhere. Then AI helps clean and organize this messy data, making it easy to understand. All right. So data is there, so much of data is there. We are taking help of AI to clean it, to organize it, so that it can make more sense. It is easily understandable. AI also uses its own creativity. And that's what we call generative AI, right? We all these days use Chat GPT, for example. So generative AI, it fills the missing parts. Like you have a satellite image, there is a cloud covered in one part of it. AI can use its own creativity to fill that part. So all the data is turned into one clear format that AI can work with. And this is called unified representation. Then you have AI tools and platforms. So smart computers are helping scientists work faster. So AI builds super smart computer platforms, right? You can think of them like big simulators, right? One cool tool is digital twin Earth. These days, the twin has become very, very common. In medical world, also, there are a lot of people who have come that they make twin health of yours, right? So they take your vital parameters, your blood sugar, your BP, etc., etc., and they develop a digital twin of yours. And then they can do experiment with that twin that if this kind of medicine is given, how your body will respond to that, right? So similarly, you can have digital twin Earth, so it's like a video game version of our own planet where scientists can run experiments. AI can also be used in robot or machines, that is embodied AI, that can go in hard to reach places. Deep oceans, one example. Okay. Then third is making and improving hypothesis. So AI help ask and test science questions. As we said, hypothesis is a smart guess or theory about how Earth works, like question, what causes earthquakes, something like this. So in past, scientists made hypotheses based on what they thought. Today, AI can discover patterns and help create new guesses from data. So it is not only based on observation, it is also based on data. So AI also helps test if these guesses are true using simulations and data. And then, of course, based on this, predicting the future of Earth. So artificial intelligence helps us forecast what's coming. So it's very fast at spotting trends and patterns. So it helps predict weather, climate change, disaster, etc. It can see connection humans might miss because we are not able to crunch so much of data in our brain at the same time. We cannot look at the patterns in the same way how artificial intelligence can. All right. So this helps government and people prepare for things like floods, droughts, or pollution. So in a very, very simple way, if you summarize this particular slide, it is AI is like a super helper to earth scientists. It watches, thinks, learns, and predicts. So it makes earth science smarter, faster, and more accurate. So this was again, I found this to be a very, very interesting slide. So I kept it here because it beautifully explains the entire concept. And then is our next one. This also kept for the same purpose because all these are putting a lot of thought in a very, very small capsule. So this image shows how artificial intelligence helps scientists to observe what's happening on the Earth and simulate or predict what might happen in the future. So it does it across different parts of the Earth system, like air, water, land, ice, living things, human activities. So it's like a smart detective that looks at all the Earth data and helps scientists make better guesses about the future. Left circle is observation. When we talk about observation, what we can see, measure, or record from Earth using satellites, drones, or sensors. Here it is divided in six parts. One is atmosphere, so predicting weather and climate, watching sunlight and clouds. Hydrosphere,
Sir,
that is water.
I'm sorry I'm interrupting. Your
Yeah.
slide is not visible. I think your document is visible.
Okay. Is it okay? No?
Now it is visible. The slide is visible.
Okay. All right. No problem. So going from observation to simulation using artificial intelligence. So these AI powered models can make more accurate short term weather forecasts, long term climate projections, and event specific predictions. Now, coming to near surface examples, which are after this brief introduction to AI, this is now the main part which we are talking about. So, first, we'll talk about resistivity inversion because electrical resistivity imaging is one of the very, very important tool which is being used. And in this particular webinar, I've just tried to pick few of the developments. Of course, in 45 minutes, 1 hour, We cannot put all the developments together. So I've just taken few. So if anything is missing, please don't think that why this development has not been taken in this webinar, because believe me, things are developing very fast in the world of artificial intelligence, and it's impossible to put them all together here. So just picked few which can be of great interest to all of us. So first is resistivity inversion. So when we talk about resistivity method, we all know that we are measuring the resistivity to understand the subsurface properties in terms of moisture content or water content, etc. Using voltage and current data. So Ohm's law, R is equal to V upon I. So we are just measuring that, multiplying by geometric factor, making a beautiful image of the subsurface, what we call electrical resistivity tomogram. Now, traditional approach for this is based on iterative optimization algorithms. It can be least square, Gauss-Newton, etc., etc. We start with a guess model, and this guess model is redefined iteratively. So we do the first iteration, the second iteration, third iteration. We keep doing it to reduce the mismatch between the observed data and calculate data. So you start with an initial guess, do the calculation. This is your calculated data, and then this observed data. Match the two. Keep reducing the mismatch by iteration by iteration. This, of course, is the technique which till date we use. This is computationally expensive, of course, sensitive to noise, and very sensitive to the initial condition. What did you assume in the beginning? All right. So the initial model when we talk about, it can take minutes to hours per inversion and make converse to incorrect solution, because it is based on inversion, and inversion will find the first model which is fitting with it, right? So that may converge to an incorrect solution. Now, resistivity inversion using neural network, what is happening, or what is the development today? What we talk about. First of all, it's neural, right? So when we talk of neural network, although most of you understand this very well, but it's like we have neurons in our brain, right? So it's like each neuron being a receptor and processor of the information, and at the same time, all the neurons being connected to each other. That's how our brain functions. Similarly, you can think of it like a computer having digital brain cells. Okay, so that is we call that neural networks, right? So you have these so-called neurons connected, transferring information and processing information within themselves. So when we talk about neural-based resistivity inversion, first of all, first step is synthetic data generation. So thousands of synthetic models of resistivity structures are created with different layering, anomalies, depth, etc., etc. So whatever you can conceive as a possible Earth model, you make a synthetic model of such a structure. And then you use the principles of physics, do the forward modeling, to simulate how each of this model will appear in the survey data, right? So you have created a model, and now do the forward modeling to see what this will lead to when you take the observation in the field. So this becomes your synthetic data generation. Then comes model training. So neural networks, that is convolutional neural network or UNet, they are trained to learn the mapping. So input is apparent resistivity data and output is your resistivity model. And now this is based on comparing your data with already trained synthetic models which are available using your neural networks. So networks learn spatial patterns and nonlinear correlation between input data and resistivity structures. Now, once it is trained, the network can invert new resistivity data sets almost instantly, okay, often in milliseconds, without iterative solving. So there is no iterative solving involved anymore. So it becomes very effective for 2D and shallow 3D problems. Only thing is that you should be able to create synthetic data of practically all imaginable models which are possible. I will come to that part when we talk about limitations of this. So if we talk about benefits are simple. You have it is fast, one shot prediction. Traditional is slow and iterative. Traditional is sensitive to initial model. Here generalizes from training data. Traditional, as I said, is prone to local minima. And that is something which is a problem with inversion. It will always converge to the first local minima it gets. Neural network inversion captures global mapping via training. Obviously, in traditional solver, it needs tuning each time. Here you pre-trained model, which is deployable in field. So these are the benefits of this approach. The architecture which is used for neural network architecture, CNNs, as I said, convolution neural networks, they are good at learning spatial dependencies in grid-based geophysical data. So convolutional neural network is like making a lot of sense of anything which looks like an image. Okay. Then are UNets. You have found out what is there in the image. So let's say you have found a cat is there in a particular image, but now you want to actually pinpoint where the cat is, right? So that is where UNet comes in picture. So especially suited for image to image translation task, converting resistivity pseudo section to subsurface models, finding out, for example, the position of an anomaly where it exists in that particular pseudo section. REST nets, which are used for deeper models with better convergence in complex structures. There are good notable studies on this, which are listed here. And I have got all these studies with me. So whoever is interested after this webinar, feel free to write to me and I can share these studies with you for your further studies. There are limitations and caution, of course. First is models may fail to generalize if test data differs significantly from training sets. Remember, it is always connecting with whatever training sets has been developed based on synthetic data. More the synthetic data, more training you have done, better will be your result. If your model, if your test data is very, very different from where the model has been trained on, then it may be a problem. It can ignore physics unless hybridized with physical constraints. And that's where PINN comes. That is physics informed neural networks. That is actually something which involves physics also, diverse, high quality synthetic training data. So these are few limitations and cautions when we talk about it. I have made this table of comparison of traditional versus AI-based resistivity inversion. I'm not going to go through this entire table. Why I make sometimes put so much of text in a particular slide? Because these presentations also serve as notes. So tomorrow, once you have this presentation with you, you can go through this and go through everything one by one. We have got the approach here, data input, output, speed. One thing is speed. The AI based inversion, of course, is much faster. We are talking of milliseconds here. Talking of accuracy, it is comparable to the or better than the traditional method. Then we have generalization, noise tolerance, uncertainty estimation, field deployment, etc. So this I'm not going to read through. It is for your reference whenever you get to this presentation. So AI inversion is faster and often more detailed, but needs careful training and validation to ensure geological plausibility. It is best used in hybrid workflows where traditional physics and AI complement each other. This is very important to understand. If we are only talking of the approach where we have just using tons and tons of data to understand patterns, we still might create a lot of problems and we might make a lot of mistakes where our observation is not from the similar kind of scenarios where we have done our synthetic generation. That's where it's always good to combine the principles of physics and then have a combined model where physics and AI complement each other. Second, after talking about ERI, electrical, I'll talk about the next one, and that is I'm in between. I take a pause because I stop videos. For now, I will request everyone to keep your videos stopped. That would be great because sometime you are not in the most comfortable situation to start your video. So keep them off for now. We'll request you to switch on your video later. For now, you can keep your video off, please. Okay. All right. So next we'll go for anomaly detection in magnetics, electromagnetic, and GPR data. So what is anomaly detection, first of all? So in geophysics, an anomaly is a deviation from expected background pattern. in a measured physical property. So, for example, you are doing resistivity measurement in a particular area. The ground is homogeneous, isotropic, everything is good, and it has a uniform resistivity of 100 ohm meter. So, practically, your entire pseudo section or your entire resistivity section will show a resistivity of 100 ohm meter. And then comes a small area which shows a resistivity of either 1000 ohm meter or 10 ohm meters, right? Now, this is very different from the background resistivity in the area. This is what we'll call anomaly. Okay, so anomaly is a deviation from expected background pattern in measured physical property. It can be resistivity, it can be magnetic, it can be dielectric constant. Okay, so what it will tell you is presence of buried structure. It can be a pipe or a tunnel or mines, geological faults and cavities, contaminant plumes, archaeological features. All these will reflect as anomalies in your geophysical data. Now, traditionally, how we are doing geophysics is that we do all the processing. We do the processing using a different software. All right. But when it comes to interpretation or detection of these anomalies, we depend on visual inspection or rule-based thresholding. So visual inspection is that we look at the anomalies. Okay, here low resistivity, high resistivity. We see, okay, this might be the boundary of the low resistivity zone, etc., etc. Okay, and then we have rule based thresholding. We can say, okay, amplitude less than this or amplitude more than this. We can generate, iso maps that, okay, just highlight the areas having amplitude more than this or less than this, etc., right? So this is generally what we do. So AI basically introduces a data driven approach capable of learning complex non-linear relationship between input signal and buried anomalies. So here again, the model is trained by a lot of synthetic data or a lot of real data where anomalies have been picked already, anomalies have been marked, and then fed to the AI for training. And based on that, it learns that what calls for an anomaly, what I will call an anomaly. And once it has got enough data to train itself, it will now start looking at these anomalies on itself and start detecting these anomalies, right? So this is one example of this, where high resolution image of subsurface infrastructure using deep learning artificial intelligence and drone magnetometry. This paper reference is here, and this is the anomaly which has been picked up using AI. All right, this is basically a pipe, and this has been picked using AI algorithm. This is a very nice paper. Anyone who is interested, as I said, please, I will send the paper to you. Okay. If you talk about the workflow, so first is data input. So raw or pre-processed GPR, magnetic or EM survey data, 2D slices, time series, or full 3D volume, you can put, that is a data input. Then goes for pre-processing, where noise reduction. You can do time gating. For example, GPR data, the first 10 nanosecond, let's say, is only having the lot of air wave and ground wave. You just want to focus on a particular depth, so you can do time gating. You can do frequency filtering. You can filter the frequency which is unwanted for you in that particular case. Data normalization, that is, you can have different kind of gains in different traces or different set of data. You can normalize the data. And then modeling. So AI models like CNNs, autoencoders, transformer architectures are trained on labeled data sets, synthetic or real. And some models even learn to reconstruct normal data and flag residuals as anomalies. All right. So these anomalies then can be highlighted on maps, depth slices, time series plots. Output can be binary, that is anomaly, no anomaly, or it can be graded, that is probability, confidence zone, etc. So this is the workflow of a typical anomaly detection using AI. We are using it, like I'm using it in real life, at least in GPR. We are using it a lot. I'm also recently started to use it on some certain magnetic data, where I'm finding it very, very useful. Even in the resistivity data, and I'm not training the model with millions of data set, okay? But for a particular site where I'm working, I'm just training it by giving limited amount of data and then using it to do anomaly detection for the remaining data set. It makes my workflow faster, more accurate. I'm able to get better results out of it. So this is something which we are doing. And there are different deep learning models which are being used, which are put here. CNNs for spatial anomaly detection for 2D, 3D, GPR, and magnetic grids. Then we have auto encoders for unsupervised anomaly detection by reconstruction error, time series based anomaly detection for moving GPR and EM surveys, object detection in redagram, which is used for archaeological GPR also, and transformer models for multimodal data fusion and long-term dependency, long-range dependency. So all these are the deep learning models which are in use. Again, a lot of details to go into that, which I'm not obviously putting here, but anyone interested in more, I'll be very happy to share with you. So if you look at application, first is GPR. So it detects underground voids, rebars, pipes, tombs. Now here, if you see, this is a very beautiful example. Now this is one hyperbola, this is one hyperbola, and these are easy to pick up, right? And manually also, it becomes very easy to pick. But look at this one here. It's very faint, all right? So AI detects even these kind of faint reflections in layered media, noisy ground condition, which human eyes can miss. So that is where it becomes very useful. So it improves the detection beneath asphalt, concrete, or clay-rich soil. Because when it comes to clay-rich soil, again, our signal attenuation is very fast. We are not able to get good amplitude for our buried anomalies. So AI becomes an added help in that. And this is another very nice example of automatic rebar detection. So these days, whenever we are doing, for example, concrete scanning, and there are a number of these ray bars, and here is the detection of your ray bars using AI. There are a lot of commercial software which are available. I don't name any software right now, uh, but there are commercial software which again enable auto detection of hyperbolas, which can correspond to utilities or which can correspond to cylindrical objects or reinforcement bars, etc. Similarly, in magnetic survey, for finding out UXOs or pipelines, deep learning improves classification of dipole signatures, clutter filtering. All this is a very interesting application. Just yesterday, actually, I was processing some magnetic data, and I wanted to, detect two pipelines in this magnetic data, and I used certain algorithms for that. And it was interesting how it really made my entire workflow much faster and more accurate than if I had done it manually. Then electromagnetic surveys, where it can separate natural variations from anthropological features like cables, etc. And it can be very effective in high noise environment like urban or coastal areas. So same thing which we have been doing manually, all right, but which becomes very difficult for us to do just by with our limited visual aids. AI comes in very handy in solving these problems. So advantages, of course, we talk about noise handling. So traditional method, manual filtering. Here it learns to ignore background noise. So more and more data set you feed, you tell what is signal, what is noise, it will automatically learn how to ignore the background noise. Speed, manual or semi-automated, right? That is in the traditional method. Here it is real time and automated. Interpretability, uh, traditionally, we always needed experts to intervene for interpretation. Here, we can auto label and rank anomalies once it comes to AI based solution. Scalability. So, in our traditional method, it is limited to field of view. Here, we can process full grids of volume, so large amount of data can be processed. Here, I have listed, some good research works which are available again, where they have used these CNNs to detect and classify buried infrastructure from drone acquired magnetometry, then autoencoders to synthetic GPR data to locate voids in multi-layered soil with 95% detection, etc., etc. Future trends are very interesting, which will be explainable AI for geophysics. For example, it will not only flag something as anomaly, it will also tell you why it has been flagged as anomaly. That's very interesting. Okay. Then edge processing, that is real-time anomaly detection directly on the UAV or field tablets. So as the data is being collected, anomaly detection is being done then and there. Imagine the significance of that. Just with one example, we are trying very hard to find out landmines, for example, all right, which are being put by Naxalites in different areas of the country. and we lose our people in the process, right? Today, if we collect the data of landmine, this data has to come back to someone to process it, and then only will be able to say whether there is a landmine there or not. In future, if we are able to go to that real-time anomaly detection, that directly then and there, it tells that, okay, data analyzed, let's say we are just doing a GPR based on a drone, and we know, okay, this is a landmine there, and that's it. We can we can save lives. And there are plenty of examples of these kind of real-time applications which will be very useful. And of course, multi-sensor integration. So you take data from GPR, magnetics, and other things, and put it in multi-layer. And I switched off my own video. All right. So this was brief about what I wanted to talk about AI. There's a lot to talk about it, but since we have limited time, so the rise of drones in geophysics, how aerial platforms are transforming subsurface exploration. This is another very interesting topic. We'll just spend some time on this. I am not doing bad or not doing good also. All right. So I'll be a little fast. Don't worry. So here, drone-based sensing system, we have modern UAVs, right? Unmanned aerial vehicles, which are serving as airborne geophysical platforms for lightweight sensors. And there you can have sensors like magnetometers, GPRs, LIDAR, EM sensors, radiometric sensors. Various kind of sensors can go with drones today, right? And that expands the possibilities a lot, because this is not requiring you to do it in the ground, and this is not based on aircraft, it is based on drone. All right. And of course, we know magnetometer, you can detect, ferrous objects, UXOs, GPR, etc. I'm not going in detail of that. And it is possible to integrate payloads combining multiple sensors for richer data sets. So it is not only that you are sending your drone there and you are only recording, let's say, one particular set of data. You can record number of data, a different kind of data, different kind of sensor data from that. This is the evolution from traditional surveys to drone-based detection technology, which is given here, starting from 1950s, how it has developed, and today we have come to AI and edge computing in drone systems. And future, of course, is swarm drones, where a lot of drones can be used together, interconnected, sharing data with each other, and that will be a great thing to happen. Here we have put comparison of sensor type used in mineral, oil, and water exploration. Includes hyperspectral imaging, magnetometers, LIDAR, thermal infrared, GPR, gamma ray, seismic. What are the application areas? What are key capabilities? What are the limitations? As I said, this is not to be read here. This will serve as notes with you. So please go through it in your time. So if we just go to a workflow diagram of data capture to AI powered resource anomaly detection, right? So here it starts with pre-flight planning and mission automation. So you decide your survey design. So let's say you're going to do, a GPR survey for a particular task. Based on that, you decide what is going to be your line spacing, how you are going to decide your entire flight path, in which direction you are going to take your grid lines, how you will optimize your coverage. All that is pre-flight planning and mission automation. Then you go to real-time data capture and georeferencing. So hyperspectral, LIDAR, magnetic data, integrated GPS is there with the system. So you can do a very, very good georeference data capture. Then AI and machine learning in post-flight analytics, you use that for image processing, anomaly detection models, feature extraction, and then the data storage, integrity, and edge processing. So how it makes so much of a difference is that accessibility. It can reach steep slopes, marshes, forests, restricted areas. The cost is lower than aircraft or ground crews because less manpower and fuel. Speed is very high because it can cover a large area very quickly compared to walking surveys. Spatial coverage is good. You can have dense grid mapping and high resolution sampling, which is possible. And it minimizes human exposure in hazardous or unstable terrain. So there are many areas where, for example, people cannot even walk there. marshy areas or difficult to reach areas. And today it has become possible to conduct surveys in these areas using our drones or aerial platforms. Just a couple of examples: drone based magnetic survey, which has become very popular. So in this, of course, we are using magnetometer, and we can cover a very, very large area very quickly. We have given the advantages here in terms of accessibility, efficiency, and speed, cost effectiveness, etc. So definitely to cover large areas quickly, and areas with a lot of undulation and difficult to reach areas, this is a very, very good tool to use. Drone based magnetic survey, it has its own limitations. So here I have listed all the limitations also, because first of all, you are flying at a particular altitude. Okay, so anomaly is going to be weaker because of the distance from the ground, right? Then you will have certain EM interferences which will come from drone motor or electronic generation, etc. There might be some limit on resolution. So there are certain limitations also, and that's why we put it here that 1 minute, just putting my windows. So drone magnetometry excels in coverage but has resolution trade-off. Use it for wide area scanning, and then in the areas where you need more follow-up, you can do ground-based follow-up, or obviously a very dense coverage if it is not possible to do ground-based follow-up. Then we have drone-based GPR, which is a very interesting development which is taking place. Here we are putting GPR with a drone, and looks something like this. So conventional methods of GPR, of course, cart-based, towed behind a vehicle, handheld, and boat, right? And now, of course, you have drone-based, which makes survey accuracy is good because your speed and position can be very, very accurate. Productivity is increased a lot. Risk mitigation for personnel, especially in areas which are dangerous areas. More cost. For example, we are using a lot of drone-based GPR in the border areas where you cannot do ground-based GPR. More cost efficient because, of course, faster coverage. And if the terrain is uneven, for example, a person or land vehicle might not even move there. This kind of GPR can work very nicely there. There are limitations. First of all, the weight limitation, right? How much payload a drone can carry. Most important is loss in penetration depth. Okay. So as soon as you put this away from the ground, your GPR antenna, all right, there is another interface which you're creating, that is air ground interface. And because of that, your penetration decreases. Flight time is limited to the battery life, which can be, sometime just 15-20 minutes before you have to recharge it. You have to have low altitude flights in GPR, because if you take it too far off, you will get all the energy being reflected from the top, and you won't be able to see much. So I will show you what height is required. And low altitude flight sometimes becomes very difficult. Okay, and you need space close to the drone, the perimeter around the drone. So you cannot do it in tight spaces like cities, streets, etc. So if you look at this table, it's a very good table describing it. So if you have, for example, a center frequency of 1000 megahertz, that is 1 gigahertz, penetration is going to be 1 to 2 meters from surface. Same penetration will come to zero point 0.3 to zero point 0.5 meters as soon as you put it on drone. Okay. And recommended maximum distance is zero point 0.3 meters from the ground. Okay. 0.3 meters, that's just 30 centimeters. So higher the frequency, closer you have to keep it to the ground. And that's a challenge many a time because of the thrust the drone creates because of the sheer pressure of the air, and is a minimum size of detectable object. And here this table I have given for various antennas, various type of antennas. Important thing to see is that penetration depth is becoming almost half compared to ground-based system. That's a very important thing to note. And if you see that the maximum distance of the antenna, 500 is zero point 0.6 meter. It has to be very close to the ground. These are important things. And that's why even today, when we talk about drone-based GPR, low-frequency drone-based GPRs are becoming effective, and they are obviously for large-scale objects, okay, large-scale mapping. Then integration of methods. It's very important to understand this point about integration of methods. I always say that always try to use more than just one method to understand your subsurface. Why? Because as an example, if you're just measuring VP, that is P wave velocity, look at this table here. All these formations, that is quicksand, clay deposit, weathered rock, all of these can have P wave velocity of 1500 meter per second. Imagine quicksand. P wave velocity is based on compressive strength, right? So even quicksand will have a P wave velocity of 1500 meter per second, where you can't put your foot there, right? So if you measure shear wave velocity at the same time, you will be able to differentiate between most of these formations, which are totally different based on their shear strength. And that is why always measure more than just one physical property. So this is a very good example where P wave velocity, Poisson's ratio, that is Vp upon Vs, density, resistivity, four parameters have been measured in one particular field. And then using AI, the depth distribution of model points have been done based on adopted criteria. That is, VP should be between this and this, VP upon VS should be between this and this, density should be between this, and our resistivity should be between this. And based on that, all the points satisfying the criteria have been marked. And these points become your the target points, let's say for drilling. All right. So this is one good application of how you can integrate data coming from different measurements and then use them collectively using the power of AI to interpret it. Now, I have tried to complete it almost in time, but my request to you is that there is so much lot to be discussed on this. So this is the conference which is coming up from 12 to 14 November in Delhi. Please be part of it and let's discuss it further in this conference. Just a small video about this conference.
Greetings. We are very excited to share that the third Indian Near Surface Geophysics Conference and exhibition is coming up this November. It is being organized by ACO Foundation Academy in collaboration with EAG. The event will take place from 12th to 14th November 2025 at the Surya in New Delhi. This year's themes touch on some of the most critical areas from engineering and environmental geophysics to urban mapping and energy transition solutions. From seismic refraction to ground penetrating radar, this conference brings it all under one roof. Two pre-conferences are also being organized on 12th November 2025, focused on dam safety and contaminated sites. We will also be presenting the most awaited INSG Awards and Dam Safety Awards for this year. So if you're working in geoscience, infrastructure, environment or research, this is where you'll want to be. Please visit our website and register now.
So this is where you want to be.
Greetings.
So please be part of this and let's meet here and talk more about it. So with this, I conclude my presentation for the day, and now I'll go for my chats and try to see what all questions we have. I'll take the questions from chat first, and after that, if time permits, we'll take other questions. So I'm just all right. Okay. All right. All right. So first question is from Mr. Manik Kumar. He said, "What will be the accuracy for drone survey underwater?" So when we talk about accuracy, there are different types of accuracy we can talk about. For example, one is of course the position accuracy. So position accuracy is as accurate as your positioning device is. So if you are using your GPS, for example, in the differential mode, it is as accurate as your DGPS is. Second is your accuracy in terms of depth. If you're talking about the measurement of bathymetry survey, which is being done using a drone, that will depend on how well you are calibrating your data. Because the speed in water, we know the dielectric in water, and but it is always good to have some calibration, so that will make it more accurate. So it is fairly accurate, as we say, when it comes to the measurement of the depth, and spatial accuracy is as accurate as your device. Okay. All right. And what else? What else? Okay, very interesting. So we do not have any more questions. I think it was quite a long session on a very new topic. So that's very well understood. Okay, one from Mr. Devendran. Are AI-based software for resistivity readily available? Unfortunately, not to the best of my knowledge. Okay, so still it is being done by individual researchers who are doing it in the research mode. I'm not aware of any commercial software which has come as of now for AI-based inversion, Mr. Devendran, right? Okay, then Mr. Jagan, what may be the extreme depth in the GPR studies apart from mineral industry? How useful for oil and gas? Okay, I'll read it. Sorry. What may be the extreme depth in the GPR studies apart from mineral investigation? How useful is it for oil and gas exploration in terms of journalist studies? So, Mr. Jagan, GPR is known as a shallow investigation tool. It is not a deep investigation tool. Its depth of investigation depends primarily on two factors: the frequency which you are using and the conductivity of the ground. If the ground is very conductive, the EM waves are converted to heat very fast and you do not have much penetration. Okay. Only similarly, if the ground is very heterogeneous, then also a lot of signal scattering takes place and your penetration suffers. So if you are talking of very, very resistive and resistive ground, very homogeneous ground, then your penetration can be great. But in general grounds, we measure the penetration of GPR in tens of meters, not even in hundreds of meters. So we are not talking of application in oil and gas exploration as such. Okay. Even in minerals and all, it is limited to top tens of meters. Sometime you can go slightly deeper, but that's basically it. If it is a theoretical question, I will say that depth of penetration of GPR can go from 0 to thousands of meters, because entire ice of Antarctica has thickness which goes in kilometers, has been mapped using GPR, because there it has just the ideal condition for GPR, but that's not the condition in the ground. Okay, so that's the answer: tens of meters, not even hundreds of meters. Okay. Then Mr. Natarajan is saying, how reliable would it be to use Gen AI in filling the gaps of geophysical data? So, as I said, AI is as useful as you train it to be. Okay. Definitely, it is doing things mathematically. If you are putting the power of physics behind AI, then it can do wonders. Or if you train it with tons and tons of data, it can do great. All right. So more you train it, more reliable it will become. Unless even what you use today every day, Chat GPT or any other AI model, it is backed with a lot of data. So more the data, more accurate it is becoming. Okay. Okay. Mr. Ahmed is asking, want to attend the conference. How will you be able to assist me in providing invitation letter to aid in visa application? So please just send a mail uh, to the organizers. Go to nearsurfacegeophysics.in, the website. Send a mail to the organizers. They'll help you with all the letter and everything. Then Parmita, for drone-based survey due to lost quality in resolution of data. Uh, your question is pretty incomplete, but as I said, in drone-based survey, you are going slightly away from the surface. So obviously, your strength of the signal is suffering because of that. At the same time, in drone-based survey, sometimes our grid is coarser than what it is in our field survey. So that way, your resolution can suffer. But if you keep the grid very tight and you take a lot of data points, obviously your resolution can be pretty good even in drone based survey. Very informative, thank you very much. How many times the processing power required for AI based processing or manually processed by humans? This is from Sanapala. That's a very good question. In fact, that is one of when we talk about, especially, let's say, magnetic data, right? The computation power required in AI based acquisition is much, much more, because here we are doing practically continuous data acquisition, right? If you talk about normal magnetic survey, you go and take data in a grid of, let's say, 20 meters, 25 meters, 5 meters, whatever it is, right? You have limited number of data points. Here you're flying and you're taking continuous data points, so obviously the data which is available for processing is very large, and so is the computational power. So you need much more processing power. Okay, Mr. Dr. Ayaz, done PhD on light magnetic. Okay, Mr. Dr. Ayaz, I would really like you to please write to me on my mail ID. I'll give you my mail ID and I'll be able to help you better because it is directly linked to some research which you are planning to do. All right, great. So with this, we come to the end of this presentation. And now I'll request everyone to please open your videos and let's have a group photograph towards the end of it. Let's have a beautiful group photograph. I can see a lot of familiar faces there. My friend Andy also is attending. Hi, Andy. Anushka, are you through with the group photographs? All right. So what I'm going to do is I'm just giving my email ID here, and any further questions about any of what we have discussed here, you are more than welcome to write to me, and I'll be very happy. And the person I just talked about, Andy, he also is one person who is using AI and ML a lot in Heliborn time domain data, where they are doing wonderful job. They are collecting the data, and then whatever drill hole data is available, training the converting it to geo model, and more data which is coming up, the model is being improved. And Andy, I think it will be a privilege for everyone to hear about it for maybe 2 minutes from you. Why not? Since you are here, and just saw you there, you can unmute yourself and just maybe just tell about it a bit.
Now.
Yep.
No, thank you very much, my friend. Yes, no, it very much connects to all the fantastic things that we've just heard for the last hour. Indeed, we are very, very intensely using machine learning, and it is really a game changer in terms of kind of the value and the richness what you can get out from geophysical data. And that spans basically throughout all of the fields, all of the various methods that we've just seen. Various different types of machine learning workflows, can be neural networks, can be classification algorithms. They give us the opportunity to bring together, truly integrate, as Dr. Rana so well said, the geological information, the geotechnical information, the hydrogeological information, whatever is relevant for the project, whatever is available, and then truly connecting that with maybe one geophysical method or various geophysical methods. And that's what we call physics based machine learning. So it's not just, using a AI black box and pressing a button and hoping for the best. It is physics driven. It still needs specialists that have the ability to control and to tune the algorithms, that they do, reliable work. And then it opens fantastic possibilities. It really does the things that we humans struggle with, right? If you think about, say, 2-3 different 3D data sets and then a few boreholes, and then your job is to make a holistic model out of them. It's almost impossible. But with machine learning, you can unlock all of that hidden information there. You can fill the gaps and get a model that is consistent and it's still based on maths. It's not just some fantasy. Yeah, it's really, really a game changer.
Thank you.
Thanks for
Thank
the
you, Andy.
opportunity.
Thank you. I'm very happy I could spot you there once we all open videos. It's a pleasure to hear from you, and it's great. I think audience also got the message. It was very crisp, but they got the message from you. Thank you very much for being here, and thanks to all
Thank
of
you.
you for being here for last 1 hour 16 minutes now. And yes, the recording will be available to everyone, and we look forward to talking to you in future. And next webinar again is on next to next Saturday. So be there. Let's be together and let's do something great for near surface geosciences. Thank you.
Thank you.